Okay, Bismillahirrahmanirrahim. So we continue our lecture with chapter 7, where we are going to discuss on this dimensional analysis and modeling. We are going to talk about what is this thing actually, its advantage, and also how to do this dimensional analysis. Okay, from this figure, you can see a scale of like 1 to 46.6 model of a destroyer which is being tested in a 100-meter long towing tank in the University of Iowa. See, the model is 3.048 meter long, so we can know the real destroyer length just by multiplying this 3.048 with 46.6. So in tests like this, the Ford number, which is a non-dimensional number, which is very important for the problem or case where you have this open surface or free surface flow like this, like water in a reservoir, in a tank, or in the oceans. They are all this kind of case where we have a free surface where it is not confined at the top, it's open to atmosphere. Okay, the objective of this study, so we are going to cover all of the objectives, right, where we are going to develop a better understanding of dimensions, units, and dimensional homogeneity of equations, where all of you have already learned this so many times in statics and dynamics. And to understand the numerous benefits of dimensional analysis, and to know how to use the method of repeating variables to identify non-dimensional parameters, and to understand the concept of dynamic similarity and how to apply it to experimental modeling. So first we go to the dimensions and units. Yeah, most of you are already familiar with this, where the dimension is a measure of physical quantities like length, mass, and time, where unit is a way to assign a number to that dimensions, like for length is meters, for time is seconds, and for mass is kilograms. So there are 7 primary dimensions, also called as fundamental or basic dimensions, which are mass, length, time, temperature, electric currents, amount of light, and amount of matter. So all other dimensions like the secondary or derivative dimensions can be formed by combinations of these 7 primary dimensions. So this table shows the primary dimensions and their units in SI and in English units. So for our this fluid mechanics, usually we only going to use the first 3 primary dimensions like mass, length, and time. Or perhaps we are going to have temperature, usually like for thermal fluid problems. But most of the time, for fluid mechanics, usually we only have this ML and T. If we use the Navier-Stokes equations, basically in that equations, it only consists of these 3 dimensions: momentum and continuity equations. So in these examples, it talks about these primary dimensions of surface tension. So here we need, this is just how to find the dimensions of this surface tension. So as we know that surface tension is equals to force over length, and force is equals to MA actually. So M is a mass, and the acceleration is the length over time squared. So if you remember the unit, it will be much easier. Whereas you know that for accelerations, the unit is meter per second squared, where meter is length and second squared is time squared, and M is mass. And length is, of course, is the dimension is length. So just dividing this, we will get the dimensions of the surface tensions. So basically, it's how we want to derive the parameter or dimensions from the primary dimensions. So the surface tensions is a non-primary dimensions, and it is derived from this mass and time. Okay, dimensional homogeneity. So see, this is very important in order to validate whether an equation is correct or not by checking the terms of each the units or dimensions of each of the terms in the equations to see whether they have the same dimensions or not. Okay, like here, this is all the energy terms. Okay, so from here you can see that these are the equations or the parameter of this U, KE, and PE. So if we check the dimensions, okay, this is what we will get. So for this, we get ML squared over T squared, and same goes to delta U. We get the same dimensions. For kinetic energy, the same dimensions, and the potential energy, we get the same dimensions. So from here, we can say that this equation is dimensionally homogeneous. So it is valid. Okay, so you need to be cautious with this non-homogeneous equation. Sometimes we might have some error when we write down the equations and without we knowing that some of the term has the different dimensions compared to others. So that equation is not valid because they cannot like plus and minus with different dimensions. They need to have at least the same dimensions or the same units for you to work on the terms in and equations. You can also use this homogeneous equations approach to check whether the equations that you memorize is correct or not. Like for example, in your exam and that you forgot, you slightly remember your equations, you can go back to this analysis and check. Do double check whether the equations that you memorize is 100% correct or not. Okay, the dimensional homogeneity of the Bernoulli equation. So in this example, it wants to check whether all the terms in Bernoulli equations have the same dimensions or not. So from here, we can expect that actually the terms or the dimensions that we are going to have is pressure. They need to have a pressure unit. So here we check. So pressure, as we know, is force over area, and the force is equals to ma. So this is m mass, and this is the accelerations, length over time squared, and this is 1 over area. So this is the dimensions for pressure. So this half of V squared, this is for kinetic, and half here is just a coefficient. It has no dimensions. So density is mass over volumes, and V squared is the length over time squared. So you get the same dimensions. And rho gz, rho is mass over volumes, gravity is acceleration, so length over time squared, and z is the height, which has the dimension of length. So we get the same dimension as well. So here we can say that okay, they are all have the same dimension. So this equation is valid. And as we can see, there is another constant here. So what is the value of the constant? So the constants need to have the same dimensions as the other terms. So the constant here must be in this dimension as well. If not, this equation is not valid. So non-dimensionalizations of equations. This non-dimensional equations happens if we divide each term in the equations by a collection of variables and constant whose product has the same dimensions as the term that we are dividing. So what will happen is that the dimensions and the unit will be cancelled. So normalized equations, it happens if the non-dimensional terms in the equations are of order unity. The equation is called normalized. This is what we have here. Here is the normalized. So everything or the dimensions becomes unity. And the non-dimensional parameters is the number or parameters which has no unit or has no dimensions, like the one that is quite popular, the Reynolds number, and third number, I believe for most of you it is quite new. So this kind of numbers or parameters, they have no dimensions or units because they are actually a ratio between several variables, and the ratio and these variables, it cancel out the dimensions among themselves, and it becomes unity, and there is no dimensions. See, this process is referred to by some authors as inspectional analysis, because it is important for you to do analysis by using these non-dimensional equations or parameters, because it will be easier for you to discuss, because a lot of things can be discussed by using this way. Is some example where we have equations of motions. This is the gravitational accelerations, where the rate of change of the distance vertical with respect to time, which is in the second order. So if you have only one order, it becomes velocity, and you have second order, it becomes an accelerations. And this is actually the projectile equations. You have seen this in dynamics actually. So all the things here, the terms here, you can read it by yourself. And yep, these are all basically explaining each of these variables in these equations. You can try to have a read on this on your slide. Okay, to non-dimensionalize the equation, we need to select a scaling parameters. So based on the primary dimensions containing in the original equations. So from these equations, we find all the dimensions of each of the term or each of the variable. I'm sorry. So z, z naught, w naught, t, g, and so t here is the same dimensions. So what we get is z which is length, time for sure is time, and here is length as well, and this is velocity, vertical velocity, which is the initial velocity, is length over time, and this is the gravitational acceleration, length over time squared. So this is the non-dimensional variables for the vertical locations and for time. Is non-dimensional height and non-dimensional time, which is equal to z over z naught. So the parameters up here will be dividing themselves to cancel out the dimensions. So we get z here, it represents the ratio between the current location of z over the initial location of z. And the non-dimensional time is a ratio between the initial velocity multiplied with time over the initial height. So the division between these will give you unity dimensions. So go back to these terms, which is for the gravity. So just substitute z here with the one that we have here. So z is equal to non-dimensional z multiplied with z naught, and here time here is equal to non-dimensional time times by z naught divided by w naught. So this is equals to this. So by just substituting them, where w naught and z naught, it is a constant. Okay, it is actually an independent variables, which when we do experiments, these are the things that we are the one who decide, and this is the consequence or the dependent variable. So the location of z and location and at the time t is depends on how we initiate the experiments. So it's equals to minus g. So by just changing this, we get this term, and this is what we call it as the Froude number. And Froude number is by the square root of this is called by as Froude number. Okay, so the Froude number is important in the free surface flows, such as flow in open channels or rivers in oceans. Shown here is the flow to a gate. The Froude number upstream of the sluice gate is FR1, and here is FR2 downstream of this sluice gate. So this non-dimensional equation of motions is represented by this. So the non-dimensional results. So we can change all of the equations. The one that here we've seen here, this is all the dimensional. So we can substitute this with the non-dimensional parameters that we obtain here, non-dimensional, and we will obtain these equations. So you just substitute. You can try to substitute the one that we have in the dimensional equations and substitute them with the non-dimensional, and this is what we will get. So if you check all of these terms, they have no dimension. Z here is equal to z over z naught, and t here is equal to ut over z. So it will cancel out all of the terms. Okay, this is another some examples. You can read it by yourself. It's too long for me to read it for you in this video. And actually it illustrates the advantage of the non-dimensionalization. If you can see here, there are so many variables, or there are so many parameters you need to consider or you need to do in doing the experiment. So you can expect there will be a lot of results, and it's quite hard to explain or to discuss and analyze your results if you have so many parameters and variables. So this is actually the results. So you can see that they have like a lot of things that you need to find here. We have a z and t, which is this is a projectile equation, the one that we've seen before. And this is when we do the dimensional approach. So we need to find the z, the height of the ball at one particular time. And we have several initial conditions, where this is the initial velocity, and this is at one space. Okay, this line represents different initial height. Okay, this is when we fix the height, initial height, and we apply different velocity, initial velocity on the ball. So you can have a lot of results here, but it is quite hard to discuss, quite hard for you to relate from between A and B. So what we can do is we can analyze them or in terms of this non-dimensional. So instead of having Z and T and W naught and Z naught, here we have Z non-dimensional and non-dimensional T, and we have a float number, where in the float number itself, it consists of W naught and Z naught. Okay, so we don't have to discuss it separately, like when we have a fixed W naught and when we have fixed Z naught. Here we discuss it all together. So here we have this specific lines is defined this float number, different float number. Okay, so when this float number, for you to change the float number, you can change it by either changing Z naught or W naught. Okay, there are a lot of more examples for you to make you have a much better understanding on this. So as we go through the slide, this chapter 7, you will have a much better understanding on what is the significance of these non-dimensional parameters. In this example, extrapolation of non-dimensionalized data. Okay, we have a gravitational constant at the surface of the moon is only like 1/6 of the gravity on Earth. For an astronaut on the moon throws a baseball at an initial speed of 21 meter per second at 5 degrees angle above the horizon and 2 meters above the moon surface. So using the example that we have before, we need to extrapolate the data. So you know that the initial velocity, which is the vertical uh, component, is actually equals to 21 meter per second multiplied with sine 5 degrees. So we get the vertical uh, velocity of that ball, 1.83 meter per second. So by substituting them into the float number, okay, but this time we use the moon gravitational acceleration instead of this Earth 9.81 gravitational accelerations. So we obtain the float number as 1.03. So you can estimate. Okay, from this actually we can find the value. Okay, it said that it asks us to find how long the ball it takes to reach the ground. So we go to fault number 1.03. So this is actually the ground, zeros here. So it is about like close to 2.75, something like that. So the T non-dimensional T is 2.75. So times is the Z naught, which is the initial height and the initial vertical velocity. So we get the dimensional T equals to 3.01 seconds. So if we use the exact calculations and we calculate the T, this is what we get, 3.05 seconds. So you can imagine how do you want to find the information, this T for example, from the graph A and B. Is it possible? It's impossible. It is possible, but I don't know. But maybe it's quite hard to extrapolate that things. But by using this, the one that we have this in the non-dimensional analysis, it becomes easy. It's just very straightforward. Just substitute all the values into what number and then see. Okay, it's goes at what time, and then we can predict or estimate the times taken for the ball to reach the ground, to hit the ground. So 3.05. So this is one of the advantage of using this the non-dimensional parameters, because you can say that it can be applied in different situations. So for example, this is when you have a different gravitational accelerations, where the one that we seen in the dimensional analysis, the one that A and B, it is only for the gravity of 9.81. Okay, in a general unsteady fluid flow problem with a free surface, the scaling parameters include a characteristic length, a characteristic velocity, a characteristic frequency, and a reference pressure difference P naught minus the atmospheric pressure. So the non-dimensionalization of the differential equations of fluid flow produces four dimensionless parameters such as Reynolds number, Ford number, Solheim number, and Euler number. So these all four are the most you could say non-dimensional parameters. So we will see these things a lot in this chapter. The Reynolds and Soho and Pratt. Euler, perhaps you will see it for some time. It's not really that popular actually. But this Reynolds and Soho is very important, especially for internal or external flow. For Froude number, it is important for the free surface flow problems. Okay, subject is 7.3, where we're going to talk about the dimensional analysis and similarity. So in most experiments, to save time and money, so tests are performed on a geometrically scaled model rather than the full scale prototype. So we create a model, usually smaller compared to the original, the full scale prototype. So to save money in this designing of fabrications. So in such cases, you must need to make sure that the experiment is valid on the model, because we want to imitate what actually will happen to the prototype just by using the model. You cannot just simply run simulations or run experiments just like that. We need to make sure there are some things that we need to consider to make sure that there's a similarity between the model scale and the prototype scale. So the three primary purposes of dimensional analysis are to generate non-dimensional parameters that help in the design of experiments, either physical or numerical, either you want to do experiments or simulations, and in the reporting of experimental results, to obtain scaling laws so that the prototype performance can be predicted from model performance, and to predict trends in the relationship between parameters. So the principle of this similarity is it must be a have this geometric similarity where the model must be the same shape as the prototype, but is scaled down by some constant or scale factor. Like when you have like you want to downscale a car, you need to make sure that all the ratio, all of the length, everything must be scale to this the same factor. And for the kinematic similarity, the velocity at any point in the model flow must be proportional to the velocity at the corresponding point in the prototype flow. So this example, we have this prototype and model. Oh, then there's the third one, dynamic similarity, when all forces in the flow scaled by a constant factor to corresponding forces in the prototype flow. Okay, for scale equivalence. So this is example where we have this dynamic, when we have this geometric similarity and a kinematic similarity, where the model, this is the real prototype, which is a building, and is your model. We need to make sure that when we scale down this, we need to scale down the others building the same as well, with the same constant. So all the ratio, the gap between the buildings need to be scaled down as well. So it's just need to make sure that everything must have the same ratio. Okay, and for the kinematic similarity, it's only will be achieved at all locations when the speed in the model flow is proportional to that at corresponding locations in the prototype flow and points in the same direction. So we have a velocity in the prototype situations and the velocity in the model situations. They are actually different. But usually when you scale down this building, the this is the size of the building for the model. Usually we require Vm to be higher to achieve this kinematic similarity. So for this you can see that all the directions of the fluid when it interacts with the body has a similar angle as the prototype. Okay, and this is the dynamic similarity. So we need to check that actually the force experienced by this model need to be scaled to check that it has similarity with the one in the prototype. We're going to learn about this more afterwards. So this is how actually we want to obtain the non-dimensional parameter. So we will let the uppercase Greek letter pi to denote a non-dimensional parameter. So in a general dimensional analysis problem, there is one pi that we call it as a dependent pi. So we give that with the notation pi 1. So we represent this dependent pi as pi 1. So you might have a lot of pi's, but the pi 1 is only reserved to those that is dependent, and the rest is independent, which the one that we set, we put it pi larger than pi 1. So this is the, for example, this is actually the things that we want to find, the parameter that we want to find, and this is as a function of this. So these are all the inputs that you put, and it will give you the output. So to ensure complex similarity, the model and prototype must be geometrically similar, and all independent groups must match between model and prototypes. So all of this pi for the model and p must be geometrically similar for the model. So for all of these different variable pi 1 until pi k. Okay, this example of when we build a model car which is a downscale in terms of size compared to the prototype car. So you can see that the LP is the length of the prototype and LM is the length of the model. And this V mu and density and V dynamic viscosity and the density has that for the prototype and for the model is not necessarily be the same. So the Reynolds number is formed by the ratio of density, characteristic speed and characteristic length to viscosity. So alternatively, it is the ratio of the characteristic speed and length to the kinematic viscosity, which is defined by nu. So nu is equals to mu over rho, where this is the kinematic viscosity equals to the dynamic viscosity and divided by the density. So for this case, see, we have this pi 1, which is the we are want to study the drag force actually in this case. It is as a function of the Reynolds number. This is Reynolds. This Reynolds number actually is a combination of all this input that you put. Where this Reynolds number is equals to rho VL over mu, where the rho we have already VL and over mu. So all of these four parameters, we combine it into one parameter, and so we only have one here. So and FD here also need to be non-dimensionalized and normalized with rho V squared L squared. So this is our dependent. This is the one that we want to find, the drag force acting on the car. And this is the independent parameter, which is the Reynolds number. Okay, we have a similarity between model and prototype cars. So we have a aerodynamic drag of a new sport car to be predicted at a speed of 80 kilometers per hour and then a temperature of 25 degrees. So we build a 1/5 scale. So basically the size of the car is 1/5 from the prototype and test it in a wind tunnel. So it is winter and the wind tunnel is located in an unheated building. The temperature of the wind tunnel air is only about 5 degrees Celsius. So you know that for air in 25 degrees Celsius and 5 degrees Celsius, it has a different properties in terms of density, in terms of the viscosity, all is changed. So determine how fast engineers should run the wind tunnel in order to achieve similarity between the model and the prototype. So we go back to here. So to achieve similarity, pi must be equal to pi. Pi for the model must be equal to pi for the prototype. So in this case, our independent variable is Reynolds number. So we need to make sure that the Reynolds number for the model must be equal to the Reynolds number of the prototypes. So go to here. So pi 2 here, the independent variable of the model, which is the Reynolds number, must be equal to the pi 2 of the prototype, which is the Reynolds number of the prototypes. So from here, you can just substitute all this, or VL and mu, so you can find the velocity is needed to run the experiment in order to achieve the kinematic similarity. So you can see that for the 1/5 scale, so you can see that the LP over LM here is 5. This is showing that the ratio between the prototype and the model size is 5 times bigger than the model. To ensure that we achieve the dynamic similarity, the velocity in the wind tunnel must reach 354 kilometer per hour. Okay, so this is how you want to do experiment. Like if we cannot do it on the prototype because the size is too big and it's very expensive to fabricate the prototype. So we need to use, like for example, a smaller scale model. But the problem is we need to make sure that for a smaller length size, we require actually a larger velocity to get the same Reynolds number. See, the problem with this is 354 kilometer per hour actually is quite high. It's close to 100 meter per second. And so as we know that for example, for this 80 kilometer per hour is like much lesser than 100 meter per second. And for that low velocity of air, the flow is still can be considered as incompressible. But if the speed is quite high, once it reach quite about 0.3 Mach number, which is about close to 100 meter per second, it is actually cannot be considered as incompressible because it already reached the condition where the flow will become compressible. So prediction of aerodynamic drag force on a prototype car. So in this example, it's follow up from the previous one. Suppose the engineers run the wind tunnel at 354 km per hour to achieve similarity between the model and the prototype. So the aerodynamic drag force on the model car is measured with a drag balance. So we use these instruments to measure the drag balance, to measure the drag of the model, which is experienced by the model. So several drags reading are recorded and the average drag force on the model is 94.3 newtons. So predict the aerodynamic drag force on the prototype at 80 kilometers per hour and 25 degrees Celsius. So similarly, pi 2 it must be equals to pi 2 and same goes to pi 1. It must be equals to pi 1. So we have the value for the model, the F force in the model, and we have the rho VL of the model. So we can translate it into the what is expected to happen on that car, in the actual car prototype at a speed of 80 kilometers per hour and with the air with 25 degrees Celsius. So from this experiment, we obtained that the drag force that is being experienced by this model is 94.3 newtons. So in the prototype, for the same situations as mentioned in the previous example, where 80 kilometers per hour and the air is 25 degrees Celsius, you can expect the drag force that is being experienced by the car is about 112 newtons. Is slightly bigger. So here for the special case in which the wind tunnel air and the air flowing over the prototype have the same properties and under similar conditions. Okay, like the one that we see in the example is where the experiment is being done in a place which is much colder compared to the one that we are planning to experiment it. Like we want to understand what's the effect of the air at 25 degrees Celsius, but we do the experiment during the winter at 5 degrees Celsius. So this is when we have the air properties in the prototype situation and in the model has the same value of properties because it has the same, for example, we conduct it at the same place. So this is what we can expect. The mu and density of the air is similar. So the one that is only difference is the length and the velocity. So this will be a little bit easier to compare. So if the two fluids do not have the same properties, the two drag forces are not necessarily the same. So for this case, as you can see, for the force, non-dimensional force is mainly depends on the rho and L squared and B squared as well. But for this, the you can say that the FDM is equals to FDP. Okay, in this situation experiment, if a water tunnel is used instead of wind tunnel, so we use a totally different fluid. Instead of using wind, we use water. So it's still possible. So to test their one-fifth scale model, the water tunnel speed required to achieve similarity is this. So from here you can see that for the model here, it use water. So Lm is basically the same, which is it depends on the size of the model, and mu m and the rho m is of water. So instead of if in the prototype, we expect to find what happens when the car runs at 80 kilometer per hour, we can do the same experiment with a model of one fifth in in a water tunnel at the velocity of the water equals to 25.7 kilometer per hour. So this is the advantage of using water tunnel, where because the water tunnel speed is much lower than the required for wind tunnel using the same size model. So we can avoid a problem where the flow to be incompressible, or the flow to be compressible in the wind tunnel just by using a different fluid, which is liquid. So the method of repeating variables and the Buckingham Pi theorems, this is the method to obtain the non-dimensional parameters, where you need to memorize all of the steps. You need to memorize the step 1, you need to list down all the parameters in the problems and count their total number and n. So you have, if you have 7 parameters, you have n equal to 7. You have 6 parameters, n equal to 6. So each of these parameters you need to list down the primary dimensions. So like for example, if length, you need to put L. If it is mass, you need to put M. If it is velocity, is L over T squared. So you need to list down each of the parameter dimensions. So step 3, set the reduction J as the number of primary dimensions. So you need to calculate K, the expected number of pi's as k equals to n minus j. So j is usually depends on the number of primary dimensions involved. So you can say that most of the problems, the maximum number of j is 3 because the primary dimension is m, l, and t. So if you, in your all parameters here, it consists of, for example, you only have m and l, in all of the parameters, you only require j to be equals to 2. If you have m, l, and t in these parameters in the step 2, so you need to use j equals to 3. And k is equals to n minus j. So if you have 7 parameters and you have 3 primary dimensions, k equals to 7 minus 3, which is equals to 4. So you are expected to have pi 1 until pi 4, which you need to remember, pi 1 is only for the dependent parameter, the one that we are looking for. So we choose the j repeating parameters and construct the pi, k pi, and manipulate as necessary. So the repeating parameters usually this actually requires you to have a lot of practice because this can be different for different type of cases. So you need to be familiar which j usually being used for the repeating parameters in step 4. And then construct k number of pi's and manipulate as necessary, and then we write the final functional relationship and check the algebra. So in this example, this is the more detailed description of the 6 steps that comprise the method of repeating variables. You can read this by yourself, make yourself understand or familiar with this. Basically, you just need to do a lot of practice for this. You have like just by doing several number of practice, everything will come by itself. You don't really have to memorize this actually. Okay, this is actually goes back to the first examples before where we obtain this fraud number. Okay, this shows us how to derive that actually. So you just need to list down the relevant parameters. So in here, usually all these will be given in the problems or in the figure. So we have a 1, 2, 3, 4, and also time. Time is not mentioned here. Okay, so we have a 5 variable z, t, w0, z0, and g. So we have 5. So n equals to 5. Then we just need to list down the dimensions for each of the term. Z, L1, T, T1, velocity, L1, T minus 1, Z not L1, and G, this is accelerations, length over time squared. So the reductions, how you want to choose J, we look at step 2, how many primary dimensions are there. We have only L and T. So J equals to 2. So number of expected pi's is equal to n minus j. So 5 minus 2, 3. So we are expecting to have pi 1, pi 2, and pi 3. So the repeating parameters is the one that you are confirmed, you are sure that these are the the independent variables, the one that we set, the one that we can manipulate. Where in this case, this is the one that decided by us when we do the experiment. We can set the initial velocity and the initial height. And gravity is constant. We seldom use this because g is not something that we can manipulate, and same goes to time. Time you cannot change. So, and as we know, our dependent variable is z. Okay, and then we go to step 5. So we start with our pi 1, the dependent variable, which is z, and just need to multiply with the repeating variables, the one that we chose in step 4. W naught, the power of A, Z naught, power of B. And then what we need to do is we need to write this down in terms of dimensions. So as we know, pi 1 is non-dimensional. So we have, like, you can write down m power of 0, L power of 0, T power of 0. Just put m as well. Just don't want to miss this when it is actually needed. So for this case, you know that it only involve L and T. So that's why this example, they just skip mass. So we know that Z, the dimension is L. The velocity, the dimension is L1 T minus 1. And it's multiplied by A1. We need to find A. And the Z naught is L and power of B1. So let's keep from here. We can solve what is A1 and what is B1. We can find them. So from here, you can find that A1 is equal to 0, and when we solve the length, we can get that B equals to minus 1. So from here, you can say that pi 1 is equal to Z, and W naught here is power of 0. So you can just remove this. And Z naught here is power of minus 1. So that's how we get this. So this is the non-dimensional parameter, the non-dimensional Z. So it's equal to Z over Z naught. So, and go to the next one, the pi 2. So pi 2 is equals to the other variable. So we have already repeating variables, W naught and Z naught. And we have pi 1, Z as well. So we have already used all that. So we have T and G left. So you just multiply the repeating variables with the non-repeating variables. So T, W naught, Z naught. And do the same things, put it here and solve one by one. Solve the length first and solve the time afterwards. And you can obtain the A and B. So from this, we can obtain when we solve the time. So we just take all the time with the power. So time from here, T power 0 equals to T power of 1 minus A2. And there's no T here. So 1 minus A2 will become 0. So from there, we can get the A. And then we solve length, we get B. So from here, you can say that we know that A2 equals to 1 and this equal minus 1. So the pi 2 is equals to W, T times W naught times Z naught power of minus 1. So there, how we obtain this pi 2. And do the same thing for pi 3. And pi 3 actually what we obtain is this. And when we modify this, this is actually the Ford number. So yeah, you need to do a lot of practice on this, and once you are very familiar with this, it will be very easy. Okay, actually, established non-dimensional parameters are usually named after a notable scientist or engineer. So, in case in the futures, when you do your research, if you found some like important non-dimensional parameters which is not yet been found, you can put that number as yourself. Like that's what happened for Reynolds number, the Freud number, Becklet number, and Prandtl number. There are a lot of numbers out there. Just from the just by doing this non-dimensional analysis, and once you found out that non-dimensional parameter is important, you can denote it with your own names if it is important. Okay, step six is step six is just need to write down back. So pi one is equals to the functions of pi two and pi three. So this is the last one. You need to put this down. So pi one is the dependent variables. It's equals to the function of the independent variables. Here, example, you can do it by yourself. Okay, this 7.5 is talks about experimental testing, modeling, and incomplete similarity. So one of the most useful applications of dimensional analysis is designing physical and numerical experiments and in reporting the results of such experiments. So in this section, we are going to discuss both of these applications and point out situations in which complete dynamic similarity is not achieved. So this is when you want to set up an experiment and correlation of an experimental data. So we consider a problem in which there are five parameters, so which is quite a lot of number of parameters, and one of which is the dependent parameter. So a complete set of experiments, which is called a full factorial test matrix, is conducted. So to do the testing, we would require like the number of parameters is five. So we have a five power of four, which is required to run 625 experiments. But by assuming that three primary dimensions are represented, which is the MLT, the mass length and time, we can reduce the number of parameters from 5 to 2, where 5 is the number of parameter we learned before, step 1, and then we obtain the J from step 3, which is a 3, where we have an MLT. So we only have two non-dimensional groups, so as a number of independent parameters from 4 to 1. So because of this, for the same um thing that we want to do in the experiment, instead of running a 625 experiment, we just need to conduct a total of only 5 power of 1, which is 5 experiments only. See, this is more like mathematical on how to know how much to know the how much is needed to reflect the same to obtain the same data. So for a 2 pi problem, we plot dependent dimensionless parameter pi 1 as a function of dependent dimensionless pi 2. The result plot can be A linear or B nonlinear. So in either cases, regression and computing techniques are available to determine the relationship between the pi's. So basically, we have like 5 experiments. So this is an experiment, for example, where we have a linear between pi 1 and pi 2. And if it's not linear, just need to find to the fitting. So basically, these things will tells you like when you want to find the result of at one location in between, you can just do the interpolations and then we can basically translate it into the dimensional parameters. So incomplete similarity, we have shown several examples in which the non-dimensional groups are easily obtained with paper and pencil through straightforward use of the method of repeating variables. But in fact, after sufficient practice, you should be able to obtain the pies with ease, sometimes in your head on the back of an envelope. So we got actually, as I mentioned, if you do a lot of practice, you will see the similar number every time. So once you go into the step one, when you see all the parameters involved, you can straight away imagine and knows what are the pies that you will get. So, right. Yeah, unfortunately, is offered a much different story when we go to apply the results of our dimensional analysis to experimental data. Okay, the problem is that it is not always possible to match all the pies of the model to the corresponding of the prototype, even if we are careful to achieve geometric similarity. So this is what is called as an incomplete similarity. So this is example that I've mentioned before. When you have a very big prototype and when you scale it down, when you want to run it in a wind tunnel, you need to make sure that, like for example, if we use the same uh, fluid, okay, air, for the same fluid, if you run on a smaller scale model, the velocity needs to be higher than the one that is being experienced by the prototype. So here we have like 16, the scale is 16 times. The prototype is 16 times bigger than the model, and all the fluid property is the same. So that means that the velocity that required by the model to achieve this dynamic similarity is 16 times the one that is being experienced by the prototype, which is 429 meter per second. And this is too high. And this is already like more than the speed of sound. And for sure, it is a compressible flow. So it's not going to experience the same thing as what being experienced by the prototype, because the prototype is only experiencing 26.8 meter per second of wind speed, where the wind is still in incompressible form during that time because of the speed is slow. So there is a problem. So what do we need to do? There are several options. So maybe we can use a bigger wind tunnel so that the model don't have to be too small with respect to the prototype. Maybe you can create a larger model so that the velocity in the experiment don't have to be that high, like 16 times compared to the prototype. Or we could use a different fluid for the model test. For example, we can use water to achieve higher Reynolds number. Is because of the properties itself, because of the dynamic viscosity and the density of water is different. But the problem with water tunnel, it is very expensive because the setup, the rigs, is hard to be maintained because there will be a lot of leaking because we use water. So we could pressurize the wind tunnel and adjust the air temperature. So we play around with the properties here, the density and the viscosity of air. If all fails, we could run the wind tunnel at several speeds near the maximum speed, and then we just extrapolate our results to get the full scale Reynolds number. Okay, so this is the example. Fortunately, it turns out that many wind tunnel tests, the last option is quite viable, the false. Okay, this is sometimes we have this when it is at very low Reynolds number, the data is not really reliable. It doesn't really reflect the same physics that is experienced by the prototype. So model truck. Oh, panjang. So in many experiments, in like we cannot really match the number. So what this is what we mentioned about this number four options, where in the experiments we can just run within this range of Reynolds number, but the one that we are interested in is lies somewhere in this region. So what we can do is we can just extrapolate it so that uh, it we can predict the results for that particular Reynolds number. So we mentioned that the importance of similarity, like in the production of Hollywood movies, even like if you see the all the CGI, actually they need to understand this as well, like to make it more realistic. And sometimes if we look at it and if we knows that okay the scale is not supposed to be like that, like for example how everything is like blown up or burned, you can see that how the fire, all the scale of the fire and explosions. usually we can say that okay, it is not logic, it is not what it should be. Like sometimes they can use like a model instead of like not a CGI, you use a model, and when the explosion is like it's too small or too big, you may know. So when you do the model, you need to make sure that all of these effects follows that scale. So there's a so that there will be a dynamic similarity. All the wind, all the motion of the fire on the model, see, it can tells you whether it is right or wrong, or it is on the same scale or not. Okay. So the next time you watch a movie, be alert for the this incomplete similarity.